So now it's time for us to turn our attention to everyone's favorite topic, and that is the orbitals. So we're going to use the orbitals in two contexts. First of all, to understand bonding. So we're going to look at two different bonding theories, and that's going to help us to understand how molecules are being put together. But then the other place that we want to be able to invoke the orbitals has to do with the reactions themselves. So we can use orbitals from time to time, and we will throughout the course, to explain why we get a particular result in a reaction or why a reaction is happening the way it is. So let's start by asking the question, what is an orbital? So at this stage of the game, your answer to that is probably that an orbital is an area around a nucleus where there's a probability of finding an electron. So an area around a nucleus where there is a probability of finding an electron. So E minus for electron. But that's not the only definition of orbital. An orbital actually is also a mathematical function. It's a mathematical function called a wave function. Now, where did this come from? This came from Schrödinger, who proposed that there was a set of equations that he could use to treat the electron as a wave. So recalling from general chemistry, the wave-particle duality of the electron. So he was treating the electron as a wave and using these equations to demarcate the energy levels of the electron in a hydrogen atom. The solutions are what we call wave functions. So the solutions to these equations that he proposed are wave functions, and we usually use the Greek letter psi to represent them. So each of these wave functions is called an orbital, and as you remember from general chemistry, we would define the orbital by a set of quantum numbers, which we're not going to need to do too much of that here. Now, in terms of the orbitals that we're going to be looking at, let's make a little chart so that we can get the lay of the land and get an overview, and then we're going to start right in. So the orbitals that we're going to think about, we can broadly group into two categories: atomic orbitals, which you've seen already, and molecular orbitals, which you may or may not have seen. For atomic orbitals, we can divide those into two camps as well. We can think of atomic orbitals as either being unhybridized or hybridized. Unhybridized atomic orbitals are things like S, P, D, and F. And of those, we're really only going to be using S and P. So I think there's maybe at some point in the course there might be a comment about a d orbital somewhere, and that's about the extent of it. So really we're focusing on S and P. For hybrid orbitals, this would include things like sp, sp2, and sp3, along with sp3d, sp3d2, and so on. But again, we only care in organic chemistry for this course about these three hybridization states. In terms of molecular orbitals, so you may or may not have seen molecular orbitals. Those are going to have a new set of labels that you may not be familiar with. So molecular orbitals can be divided into three categories. You have bonding orbitals, you have non-bonding orbitals, and you have anti-bonding orbitals. The labels that we're going to put on these orbitals are as follows. Bonding orbitals will have a designation of either sigma or pi. Non-bonding orbitals are usually denoted with a small n, and anti-bonding orbitals we're going to call sigma star and pi star to distinguish them from the bonding orbitals. So the first answer to the question up above, what is an orbital? Probably the first thing that most of us came up with was an area around a nucleus with a probability of finding an electron. And that gives rise to the shapes that we're familiar with of the orbitals. So those shapes and that probability distribution comes in directly from the square of the wave function, psi squared. So remember, the wave function itself The orbital wave function is psi. When we square it, not scare it, we don't scare orbitals. When we square the wave function, we get psi squared. That's what's proportional to the probability of finding the electron in a particular region of space around a nucleus. So let's take a look at a coordinate system. Now, the coordinate system that I have drawn over to the right, before we get too far ahead, is also showing us a drawing convention that we'll use in organic chemistry when we draw molecules in certain instances. So the y and the x axes are in the plane of the paper. The z-axis, as you know, is coming out towards you and extending behind the page. So it's perpendicular to this plane. So this dashed line refers to a line that's going behind the plane. And the bold line refers to a line that's coming out of the plane toward us. Okay, so let's put an orbital on this coordinate system, and that's a spherical orbital, so you know that that's going to be an s orbital, because that's the characteristic shape of an s orbital, is a sphere. The origin represents the nucleus. Now let's think about this s orbital. Now, it's not telling us whether this is a 1s orbital or a 2s orbital, but let's think about what the differences are between a 1s orbital and a 2s orbital. So first of all, a 2s orbital is larger than a 1s orbital. And it's also higher in energy. Than a 1s orbital. So a 2s orbital is larger than a 1s and higher in energy than a 1s. So if we were to draw pictures of the two, so here's a couple of s orbitals, a 1s and a 2s, with the size difference a bit exaggerated. There's another difference between the two that we can think about and that we'll push on a little bit later. And that is the presence in the 2s orbital, but not the 1s, the presence of what's called a node. So what I've done is draw a dashed line within the 2s orbital, and that represents the node. This node, in particular, is what's referred to as a radial node. Now, what does this look like? Well, imagine the 2s orbital is a basketball. So the outer surface of the 2s orbital, that yellow sphere that I just drew, pretend that's a basketball. Inside the basketball, imagine that you could suspend an orange, and that somehow you could just suspend it in the middle so that it wasn't touching the inside of the basketball. The orange, the surface of the orange, is the radial node that I've drawn in the picture. Now we'll talk a little more about nodes later on so that we know what they are and what physical significance they have in orbitals. But for now, let's do a little more review. Let's talk about electron occupancy diagrams and the rules that we would use to put a set of electrons into one of these diagrams. So you've done these diagrams before, and as you might remember, you'll have a set of orbitals that increase from bottom to top of the diagram in energy. So the ones at the lowest part of the diagram are the lowest in energy, and as you work your way up, the orbitals get higher and higher in energy. So we're going to do a diagram like this, again, just by way of a quick review, for what we call a ground state carbon. When we say that something is in the ground state, whether that's an atom or an ion or a molecule, that means that all the electrons contained within the structure are in the lowest energy possible orbitals. So when that's true, then we would say that the chemical species is in the ground state. That's as opposed to what we call the excited state. And the excited state is not the ground state. So all this means is that not all the electrons are in the lowest energy available orbitals, or in lowest energy orbitals. So a ground state carbon atom has 6 electrons in it. And so we're going to put them into this diagram. And in doing so, remember the rules that we would use to correctly fill up the diagram. And those rules are the Aufbau principle, Hund's rule, and the Pauli exclusion principle. So we start by putting the first electron in the lowest possible orbital, lowest energy possible orbital we can get it into. That would be the 1s. So we're always starting in the 1s. Remember that we designate the electrons, or represent the electrons, by little arrows, as I've just done. So what we've done here is observe the Aufbau rule. Aufbau is a German word that means to build up. And all the Aufbau rule tells us is that we start by putting electrons in the lowest energy orbitals and working our way up. Okay, so the second electron of the 6 that we need to put into the diagram is also going to go into the 1s orbital, but we're going to draw it differently. We're going to draw it as a little arrow that's pointing down. That's observing the Pauli exclusion principle. So when we draw the arrows that represent the electrons either up or down, that's representing a quality called spin. And so the Pauli exclusion principle tells us that when there are 2 electrons in an orbital, their spins are what we call paired. Meaning that they're not both pointing up or both pointing down, but instead one's up and one's down. Okay, so now we've completed the 1s. Now before we put the other electrons in, let's remember some terminology. All the orbitals that share the same principal quantum number. Now the principal quantum number, remember, is the number in front of the orbital designation. So it's the 2 in 2s, or the 3 in 3d, and so on. So all the orbitals that have the same principal quantum number make up a shell. So we have the shell corresponding to principal quantum number 1, and a shell corresponding to principal quantum number 2. Within each shell, you can have subshells. So the subshells are the various orbital types. So in 1s, there's just an s orbital, but in the 2 shell, we have s and p orbitals. Those represent the subshells. So you have this s subshell and the p subshell. Okay, so now let's continue putting electrons into the diagram. The next 2 electrons are going to go in the 2s. So 1 up and 1 down, and that leaves us with 2 more. And so we're going to put the 5th one in one of the 2p orbitals, and then the next one we're going to put in a different 2p orbital. So this is following Hund's rule. Hund's rule tells us that when we're filling a subshell, each of the orbitals in the subshell gets 1 electron before you can start pairing. So you don't pair until each of the orbitals in the subshell has 1 electron. Okay, now let's look at the 2p orbitals. Notice that the 2p orbitals all have the same energy. In chemistry, the term for this is that they are degenerate. So the 2p orbitals all have identical energies, which makes them degenerate. Okay, some other terminology that we're going to be using throughout the course. When we refer to an orbital as being occupied, that means it has 1 or 2 electrons in it. So an orbital is occupied if it has 1 or 2 electrons. An unoccupied orbital has no electrons. It's empty. And then finally, any orbital, and it doesn't matter what kind of orbital it is. It could be an atomic orbital, a molecular orbital, a bonding orbital, an antibonding orbital, a hybrid orbital, an unhybridized orbital. All of them have the same requirement, and that is that they can hold a maximum of 2 electrons. Okay, now let's press a little bit on this idea of nodes, and we're going to talk about something else called phases. So let's look at these pictures of s and p orbitals to understand these ideas. Now the s orbital is a sphere. Okay, it just has one part. But many orbitals, as you know, starting with the p orbitals, but this extends to the d orbitals and the f orbitals as well, many orbitals are made up of different segments, like the p orbital. These segments are called lobes. So for example, the pictures below, here's a pz orbital because it's directed along the z-axis of the coordinate system, and it has 2 lobes, just like the px and the py. So the segments of an orbital are called lobes. Now let's draw a picture. So here's a p orbital. Now people are going to have a lot of different ways of drawing this. Typically it looks like a figure 8 or a dumbbell or something along these lines. Now I'm going to color in one of the lobes, and then I'm going to draw a plane, and this plane is between these 2 lobes. Okay, so the lobe that I've shaded is on top of that plane. The plane is perpendicular to the page, and the lobe that I did not shade is below the plane. The plane itself is a node, and it's called a nodal plane. So on the previous page, we saw radial nodes. Nodal planes are a different kind of node, and we're going to see those a lot more than we'll see radial. Okay, now where does this come from, and what does it mean, and why did I shade one of the lobes of the p orbital and not the other one? Okay, so let's look at an example of a wave function. So we're just going to make a little plot. So here's 0. These are positive values above this line, and these are negative values below it. And then we're just going to draw the beginning of a sine wave. Okay, so that's a wave function. Now the places above this line, the function has values that are positive. Below, the values of the function are negative, and then that repeats as the wave propagates. These points right here, though, where the sign of the function is changing from positive to negative or negative to positive, that is to say, the value of the function is 0, these are nodes. So a node is a point in a function where the value of the function is 0. Okay, now let's apply this to the 3-dimensional pictures of orbitals that we're used to thinking about. So these positive and negative areas that we just talked about briefly in the context of this very, very simple wave function, and the nodes themselves are all going to come across when we square the wave function and get the 3-dimensional pictures that we're used to seeing. Okay, so first of all, when we square a wave function, it's not like squaring a number. There's a set of mathematical processes that you have to go through, and that's way beyond the scope of the course. So we're going to take that part on faith. We're going to assume that the people that are doing the math are doing it correctly and giving us the results that we see that we can use. So that's one thing. Squaring the wave function means that all the positive areas of the function and all the negative areas of the function are also going to show up in the three-dimensional orbital picture. So that's why we shaded one of the lobes and not the other lobe in the p orbital. The shading in the p orbital represents the phases. So I'm going to make this more general. The shading in an orbital picture represents the phases of the orbital. So the different lobes of an orbital are going to be in different phases. Now, one of the phases will be positive, another phase will be negative, and so on. We don't really need to worry too much about that. Okay, so sometimes what people could do is draw a p orbital and say this phase is the positive one and this phase is the negative one, like so. But we're going to be using the positive and negative symbols to denote charge, and so we don't really want to go there. So instead, we're just going to shade the lobes, and the shading conveys the message that one lobe is in a different phase than the other one. We're not really too concerned with whether they're in the positive or the negative phase, just that they're in different phases. So notice on the wave function that anytime you go from a positive value to a negative value, you're going through 0, and that's a node. The node comes across in the three-dimensional representation of the orbital as either a nodal plane or a radial node or something like that. So the phase of the orbital refers to the phasing of each of the lobes. That's going to be positive or negative. So that comes from the sign of the wave function. A node is an area where the sign of the wave function is changing from plus to minus or minus to plus. And the value of the function there is 0. So then what is a node? What's the physical significance of a node? A node in an orbital, and now we're talking about the three-dimensional pictures that we're used to seeing, a node is an area where there is a 0 probability of finding an electron. So a node in an orbital is an area where there's a 0 probability of finding an electron. Okay, now let's go back up and look at this picture of the p orbital up here, up at the top. Okay, so let's say that the p orbital has an electron in it. One of the questions that comes up is people wonder, well, how is it that that electron can move from one lobe to another lobe since there's a nodal plane between the two lobes? Okay. Now, the question, actually, the answer is within the question itself. So, first of all, when we think about electrons in terms of orbitals, we're thinking about them as waves. Okay. If we were to think about them as particles, then you could imagine a particle moving from one position to another. But a wave doesn't act that way. So, the electron, there's a probability that it's in one lobe or the other, but it's not traveling back and forth between the two. So the way to think of a node, perhaps, is to think of a guitar string. So think of holding your finger on the string of a guitar, on the neck of the guitar, and then plucking the string on either side of where your finger is. The string is going to vibrate on either side of your finger. Okay, those are the two lobes of the orbital. Where your finger is, though, there's no vibration. That's a node. So this is called a standing wave. One of the things that we want to use orbitals to understand is bonding. And as it turns out, there's going to be two major bonding theories that we're going to consider. The first one is called valence bond theory, and the other one is called molecular orbital theory. So let's start with valence bond theory and define some terms. The premise of valence bond theory is that bonds are formed by overlapping atomic orbitals. So you have an atomic orbital on one atom that has an electron in it, and an atomic orbital on another atom, also with one electron in it. Those two orbitals overlap, and then the electrons are shared between the nuclei of those two atoms, and that's what makes the bond. Now we could be talking about unhybridized atomic orbitals, so s or p, or hybrid atomic orbitals like sp, sp2, or sp3. It doesn't matter. Valence bond theory will treat them all the same way. So let's draw a picture. If we were to describe the bonding in H2 using the valence bond model, here's a Lewis structure of H2. Remember, we got to that by envisioning the Lewis dot symbols for the two hydrogen atoms involved in the bond. So now let's draw the orbitals that are associated with this. So each of the hydrogens has a 1s orbital that contains its single electron. Here's the nucleus. And so they each have that. And so for these to bond, what's going to happen is that those orbitals will overlap. Now that's exactly what it sounds like. So just imagine those two spheres moving towards each other and coalescing, such that there's a shared area between them, and that's the area occupied by the electrons. So the electrons shared between the nuclei is the result of the overlapping orbitals, and the overlapping orbitals with the electrons in them make up the bond. Okay, so this is the whole premise of valence bond theory. So now let's push on this idea of overlap, and we're going to bring back our ideas about the phases of orbitals. So the more overlap you have, the stronger the bond between the two nuclei. So once again, here's a couple of s orbitals that are overlapping, and the part that I just colored in yellow, that's the region where they're overlapping. So let's imagine a few different combinations of orbitals. So let's say with this first example, upper left, we have a p orbital and an s orbital. So just imagine moving those orbitals together so that they're closer and closer, such that they overlap in a fashion similar to what is shown in the picture up above. As you do this, we have to think about the phases. So remember, the p orbital is in two different phases. Each of its lobes occupies a different phase. The s orbital, as it overlaps with the top lobe of the p orbital, they're in the same phase. We would call that a bonding interaction. So the bonding interaction results because the orbitals are in the same phase in that region. But as you push that p and s orbital together in that way, notice that the other lobe of the p orbital is not in the same phase as the s orbital. We call this an antibonding interaction. Which is the result you get when the orbitals are in different phases. Okay, so what's happening here? So if you had two nuclei, one with a p orbital and the other one with an s orbital, and you brought them together in the manner that we just looked at, you'd have a bonding interaction and an antibonding interaction. The two would cancel each other out in this case, and so the net effect would be that you would not get any bonding between those two nuclei. Let's move our attention to the structures on the right, or the pictures on the right. So now we just tipped the p orbital over, and we're going to bring the p orbital and the s orbital towards each other in this fashion. So we're moving the p orbital this way and moving the s orbital that way. So here what we see is that they're in the same phase, and so we have a bonding interaction, and that's not going to be offset by any antibonding interactions. So this gives us bonding. The net result here is that those two nuclei, if their orbitals approach each other in that fashion, are going to be able to bond. Let's look at the third example. So that's a lot like the one directly above it. If we bring these orbitals together, so the one on the left we're going to push right, and the one on the right we're going to push to the left. As we bring them closer together, we have a bonding interaction. But we also have an antibonding interaction. And so again, the result here is that we get no net bonding. So finally, let's look at this example, this last example. Two p orbitals that we've tipped on their sides in such a way that lobes that are in the same phase approach each other. And so again, here we have a bonding interaction that's not offset by any antibonding interaction. So two atoms approaching each other in this way, with their orbitals aligned in this way, are going to be able to bond with one another. Let's think about some terminology that we're going to be using from time to time, and that is sigma and pi bonding, which you probably have already seen. So we can describe bonds in various ways, and one of the ways is to describe the bond based on where the electrons in the bond are. Now, electrons in a bond, or electrons in a lone pair, or what have you, oftentimes we'll just describe this as electron density. So the electrons in the bond we'll just describe as electron density between the nuclei in the bond. The shortest distance between the two nuclei is called the internuclear axis, or the bond axis. So we're going to use that as our reference point. So let's say we have a sigma bond. So what I'm drawing on this bond axis is an electron cloud that shows the position and the location of the electron density in the sigma bond. So this is what defines a sigma bond. A bond is a sigma bond if the electron density is along the bond axis. Now, it doesn't have to be evenly distributed along the bond axis. It could be skewed towards one of the atoms or the other because one of the atoms might be more electronegative than the other one. But it's going to lie along the bond axis. By contrast, in a pi bond, you have two areas of electron density, and those are on either side of the bond axis. So in a pi bond, the electron density is on either side of the bond axis. Okay, so you might also remember, using this terminology, that we can talk about the components that make up a single, a double, and a triple bond. A single bond has only a sigma component. A double bond has a sigma component and a pi component. And a triple bond has a sigma component and two pi components. So in the next video, we're going to continue our discussion of valence bond theory by looking at the hybrid orbitals, how we get to them, and how we're going to use them to describe bonding.